Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is very interesting: Silyl ether protection and deprotection. So this is a part of silicon chemistry, so we shall learn about it and its application, like protection of primary means protection of alcohol, and finally its deprotection. So in this video we shall learn the basic concept, reaction mechanism, many examples and one MCQ. So before going to details, the MCQ is in front of you. So this is the question. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words for your explanation. And don't worry, at the end of this discussion you will get the right answer. So now let's go back to the main discussion. What is actually this silyl ether protection and deprotection? So in this case, what happened, this alcohol is first converted into this silyl ether. So this is actually silyl ether in presence of trimethyl silyl chloride or chlorosilane, or this reagent specially named as TMSCl, because trimethyl silyl chloride, and obviously some base is needed, and later on, so whenever this alcohol is needed, it is deprotected, and actually I shall discuss 4 methods for this deprotection also. So let's go stepwise. So first, the use of this silyl ether chemistry, that is alcohol protection. How this reaction happens? This actually alcohol reacts with this chlorosilane in presence of base and produces the final one. Question: how this reaction happens? First, the lone pair on this oxygen atom act as nucleophile, and via SN2 type reaction it leaves, and ultimately this intermediate is produced. Now if you look at little carefully, you can see that this oxygen is carrying a formal positive charge. Why? Because the alcohol was a neutral nucleophile. So after this nucleophilic attack, it's carrying this positive charge, and in order to convert these alcohol into this silyl ether, base is needed. And what is the role of this base? This base abstracts this proton such that the cationic charge could be neutralized, and later on this base is converted into base H plus composite. Now in this way, this final silyl ether is obtained. So in this case, it is actually SN2 type reaction. Now question: what type of base is suitable for this reaction purpose? Because base is responsible to abstract this proton and ultimately convert this. Now if you look at little carefully, that this oxygen is carrying a positive charge, means this oxygen, which is actually a significantly high electronegative atom carrying a positive charge, and that oxygen is attached to this hydrogen. So polarity of this hydrogen is significantly higher. So here we can say a weaker base is enough, but it should be non-nucleophilic or specific proton scavenger. Fine. So in this case, how the reaction starts? If you look at, first this lone pair on this oxygen attacks here through SN2 type process. Fine. Now if you use a nitrogen containing base, like nitrogen also belongs to the second row element like oxygen, so then there may be a competition. Competition means, for example, if you take a amine NH2, then like this lone pair of oxygen, this nitrogen lone pair can also attack and do the same job, and ultimately it can result in RNH SiMe3. This is also possible as a byproduct, but we don't want. So what possible? Amine can act as a base, it's true, but its nucleophilicity is problematic, and for that purpose, or more specifically in order to reduce or stop the nucleophilicity, steric protection is essential. Means attach big groups with this nitrogen such that it can only act as base but not nucleophile. I shall give some example. So this is, so in this case, a specific proton scavenger is needed, means the molecule or base specifically abstracts proton, not it can act as nucleophilic. So that's why this term non-nucleophilic or specific proton scavenger is provided, and that is done by this steric protection. Now, what bases are used for this reaction? For example, one is that last time we discussed this bulky base. This is 2,6-lutidine or 2,6-dimethylpyridine. See student, because of the presence of this 2-methyl group in the ortho position of nitrogen, this nitrogen can only abstract proton. It can't act as nucleophile. So that's why you can consider this is acting as a specific proton scavenger. But this second example, that is imidazole with excess DMF as a solvent, it is little different. Why I am saying? We know imidazole act as a base by the lone pair of this nitrogen, and in this case what is taken, this DMF actually in excess. Solvent means it is taken in excess, it is not in stoichiometry. So this excess DMF, what it does, first these pyridine nitrogen this imidazole lone pair act as nucleophile, means it attacks the silicon center, this Cl leaves by the similar mechanism, and it produces these imidazole silicon attached intermediate. Now question, sometime before I told that this nitrogen silicon bond if formed, that is a problematic. Isn't it a problematic case here? No. Why? Because this bond nitrogen silicon in this case, it is not that much stable, because it is a relatively good nucleophile, good leaving group. Why? Because just consider when this alcohol oxygen attacks here, so what will happen, this will leave because the leaving group is neutral. So overall what happens, the hydrogen from this alcohol is attached here, and from the beginning the chlorine, so this chlorine is here, so it is actually abstracted, the HCl produced in the during the ether formation reaction. And by the way student, remember this imidazole is a very unique molecule, because it can act as a base as well as it can act as a nucleophile, but the intermediate produced here, which makes this reaction easier or which reduces the energy of activation for this alcohol molecule to act as nucleophile. Okay, so it is a moderately nucleophilic good base. And another thing, the bond between nitrogen and silicon is not that much stable here, so that's why in this case nitrogen is acting as nucleophile as well as base. And by the way, similar concept is observed during acyl nucleophilic substitution on this using pyridine as a base. So in that case what happens, the first pyridine reacts with acid chloride, and ultimately one intermediate produced, which is further attacked by nucleophile like alcohol, and which ultimately result in ester. By the way, I have already discussed a dedicated lecture on this concept. I suggest you student, please visit if you have any issue in understanding. Now another very good example or reagent student is silyl triflate, okay, and hindered amine base for silyl ether preparation. I guess you have understood why hindered word I have given, because this is sterically protected such that this amine can't act as a nucleophile. So here obviously alcohol will act as a nucleophile like this previous one, so it will attack the silicon center and it will leave, and like the same process, first this will be generated, then amine like triethylamine will abstract, everything is same here. Now what is the uniqueness? Uniqueness is this part, triflate. Now why is triflate a good leaving group or stable? Because with whom I am comparing, chloride versus triplet. See, chlorine is a very widely available cheap atomic group, chlorine to chloride, so it's a very easy, but this triflate you need to synthesize, it's a big group, unique. So question, what is the speciality? The speciality is that it's a very good leaving group. Why? See, this part, if you compare this with bisulfate, means first salt of sulfuric acid, so everything is same up to this part. Okay, what is the difference? The difference is that first case OH is replaced by CF3, and we know CF3 is a very good electron withdrawing group because of its minus I effect, which is produced because of this 3 fluorine atom attached to carbon. So that's why these anion means this this conjugate base of trifluoromethane sulfonic acid or triflic acid is student highly stable. Okay, so if it is highly stable means this is a very good leaving group, so it leaves very easily. Okay, and by the way, one information I am giving student, this trimethyl silyl chloride has another application, that is silylenol ether formation. Similar, like first what it does, one very strong base is used like LDA to generate the enolate, and then the enolate is reacted with this TMSCl. So in this way enol ethers are produced, and I have already discussed a dedicated lecture on this topic, so please visit for better understanding. Fine. So this way what it does, this enol ether is trapped using TMSCl, but for that purpose I told a base needed which will generate the ion like LDA or lithium diisopropylamide. But instead of TMSCl, if this TMS triflate is used, only ketone is capable, because this TMS is such a good leaving that the lone pair of ketone is capable to attack this silicon center and this triplet leaves. So that's the uniqueness of this reagent, please try to remember. Now the second question, what is the acidic nature of trifluidic acid? Student, it's a very strong acid, or if in one word if I say, it's a super acid. By the way, I have already discussed few lectures on super acid. You may visit. Its meaning is it's a very strong acid, means the conjugate base is very stable. Okay, so now let's come to the next question. Driving force for silyl ether formation. Why this reaction happens? Why this silicon chlorine bond is converted into silicon oxygen bond? Actually, the silicon oxygen bond is stronger bond. Why this is stronger? Because the silicon is a second row element, and oxygen is a second row element and silicon is a third row element. So second row third row overlap is the main driving force. So not only that, see here you can see this is actually a single bond or sigma bond, but this oxygen silicon bond is significantly strong. Why? Because the field p orbital of oxygen, this electron could be delocalized into the energetically accessible vacant d orbital. I repeat, energetically accessible vacant d orbital. So this is the d orbital. So these electron donation from oxygen to silicon possible. So that's why you can consider this is actually a partial double bond character. So because of this partial double bond character, this is stabilized. Fine. Now another question may come in your mind that, sir, chlorine has also a lone pair of electron, more specifically if I say 3 lone pairs of electron, you can see here. So why it can't form stable bond with not oxygen, sorry, this is silicon. Okay, although both belongs to the same row element, because chlorine is third row element, silicon is also third row element, because student, the extent of overlap is poor for this silicon chlorine bond. And it's true that this chlorine has vacant p orbital, but extent of overlap is less like this oxygen and silicon, because 2p3d overlap is very good, so bond is stronger. So that's why silicon prefers oxygen over chlorine, and that is the reason in nature you will find lots of silica or sand. And by the way, this is not double bond, this is single bond, silicon oxygen single bond, which is associated with partial double bond character. Now, so we have understood about the importance, why it happens so efficiently. Now what is the modification on the reagent side? Okay, so this is trimethyl silyl group or TMS group, and another is triethyl silyl. So this another is dimethyl 1 tertiary, just dimethyl tertiary butyl or tertiary butyl dimethyl silane. So this, so from here how long you are going, what is happening? So bulkiness actually increases. Okay, so that is happening, and that is reflected in the chemical reaction too. I mean the reactivity or rate of reaction using TMS versus this TIPS, means triisopropyl silane, has a difference. It has some problem as well as advantages. But before going to details, I request you student, please look at this group. This you can see. Now these big groups you have seen, but look at here. This is actually protection of a 1,2-diol. Okay, and in this case this is actually protection of 1,3-diol. So that is also possible using silicon based reagents. Now So if you look at little closely that what reaction actually happening, alcohol is acting as a nucleophile and attacking this silicon center. So in this way reaction is happening, SN2 type process, and ultimately this silyl ether is forming. Now two option, either if this R1, R2, R3 are bulkier, so this direction, then rate of reaction reduced, point number one. Second thing, if R becomes bulky, then also rate of reaction reduce. Now it has both advantages and disadvantages. Why? For example, if you check this silyl ether formation, if you increase the bulkiness, it's for ether formation difficult. So you can selectively silylate a particular alcohol. For example, you take a bulky reagent and you have kept primary, secondary and tertiary alcohol in the reaction medium, and you give milder reaction condition. In which alcohol you expect this silyl ether formation? Obviously the primary, because it is less bulky, so it can react with more bulky reagent efficiently. Not only that, if you look at the hydrolysis or deprotection of silyl ether to alcohol, if these R1, R2, R3 are bulkier, then this hydrolysis will be difficult. So it means it's more protected. So selective hydrolysis of a particular silyl ether also possible using this strategy. I shall come after some time with few particular examples. So just accept this information which will be needed after some time. Now, so the question is, silyl ethers are selective reagent for alcohol and enol protection, and this enol means this is student. So this is a simple alcohol, this is an enol. So this double bond is the difference, en plus ol. Okay, so we shall learn about this. So this is we understood. Now if you have a multifunctional alcohol or multi-hydroxy alcohol, polyhydroxy alcohol, so can you selectively silylate a particular hydroxyl group? Actually this is difficult. Why? In any solvent if you take, then there is a chance. Chance means if you take a diol, then you can expect that means 50% is, you can expect statistical factor, monosilylation, 25% is disilylation, and 25% is no reaction. Okay, so this is possible because you can't decide that much accurately that okay only one silyl group will react. So but this could be achieved using a single modification, that is reuse of the reagent or solvent. You can consider here, that is THF or tetrahydrofuran, and using this tetrahydrofuran, selective silylation of one particular hydroxyl group is possible. And student, please don't get confused, these both hydroxyl group are inside the same steric environment, or they are associated with similar kind of bulkiness. Okay, so not only this, in this case this NaH sodium hydride is acting as a base, and then second case butyl lithium is acting as a base, and in both cases you can see the THF is used as solvent and the yields are from 75 to 79 versus 88%, simply significantly good. Now what is the role of this THF for this selective monosilylation reaction? There are mainly two roles. First, kinetic deprotonation of the first anion, obviously acid base reaction, but the most important thing is the insolubility of the monoanion. Means whenever this monoanion will be produced by deprotection, means O minus first, then it is not soluble in THF. So it is not possible for the further next reaction, means next anion formation is not possible because it is not in the reaction medium, it is not in the soluble form, so it can't react with additional base molecule. So that's how selective oxygen anion formation possible, and that selective or oxygen anion reacts in the next step with this TBSCl. Okay, so in this way this silylating reagent selectively silylates a particular alcohol. Now, so let's come to the alcohol protection versus deprotection and versus the steric effect. Now here ease of deprotection, if you look, then usually the more reactive silyl ether could be removed selectively in presence of next one with more bulky group attached to silane. Means that more bulky group attached will be hydrolyzed less efficiently compared to the less bulky one. So if you give a particular or moderate condition, less bulky one will be selectively hydrolyzed. That is the thing. And additionally, from alcohol side also, bulkiness plays an important role. As I told, this tertiary alcohol means more bulky, so it will be deprotected later compared to primary one. Okay, so that two factors are actually responsible. And in this case, for the removal of silyl ether to get the final alcohol, 4 methods are actually available. First one is acid mediated method, acid mediated silyl hydrolysis, and second is base mediated. Now let's learn one by one. In case of acid, what happens? This lone pair of oxygen act as a base and protonate this H plus and ultimately form this cationic species. These cationic species undergo hydrolysis where water acts as a nucleophile and final alcohol is produced. Now a question may come in your mind that, sir, these lone pair of oxygen, where it will attack, means which position? So either on this carbon or silicon atom. Student, it depends on the bulkness around the atom. Means if a particular atom like silicon or carbon is bulky, so it is more protected, so less prone of nucleophilic attack. And by the way, student, I request you, if you have any knowledge about neopentyl system, so this is actually a neopentyl system, neopentyl halide. These all are CH3, 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 and this is CH2. So this hydrolysis, or you can say nucleophilic substitution of this neopentyl halide follows which pathway? SN2, SN1, or mix of both SN1 and SN2. Please write in the comment box. I want to get the answer from your side. Okay, so in case of base mediated, how the reaction happens? Simply this base is actually acting as the nucleophile. So where it will attack, this carbon side or silicon side, depending on the bulkness. Same answer. Now, so and for that purpose, you can see in acidic medium the relative resistance for hydrolysis is, see the TMS resistance is 1, means it's minimum. Maximum is this tertiary butyl diphenyl silane, means bulky one. In between this means after trimethyl silane, next is triethyl silane, another is tributyl silane. So this thing, fine. Now, so in this case, this TBS means this tertiary butyl dimethyl silane. Sorry, I made mistake. Now, similar kind of trend is also observed in basic media, but there is slight difference. But remember one thing, student, common statement, that bulkness more, hydrolysis is difficult. Now, the method I like very much is fluoride mediated Silyl Ether hydrolysis, and this is the method number 3. Acid and base 1 or 2, third. In this case, what happens, student? This is very much selective because fluoride acts as nucleophile, attacks the silicon center, and it leaves. It produces RO minus, and later on it get proton from the solvent and produces this ROH, parent alcohol. Now question, generally we have observed that fluorine is not a good nucleophile. So how this reaction happened? And in this case, I have shown that fluorine will attack the silicon center selectively. Why? Means what unique stabilization this silicon fluorine bond is getting. That's why fluorine attacks the silicon atom. This is because the overlap. Just remember sometime before I told how this silicon oxygen bond is stabilized because of this p pi d pi. So this is the p pi, this is the d pi back bonding. Means the electron will flow from oxygen to silicon and in this way stable. And oxygen belongs to the second row element, silicon third row element, 3D, vacant 3D. Similar case is true for fluorine also. Fluorine also second row element and silicon third row element. So overlap is similar. Not only that, student, look at the information. Silicon oxygen bond energy is 108, whereas silicon fluorine bond energy is 135. So this bond is, student, relatively more stable. I repeat, relatively more stable compared to the silicon oxygen bond. So that's why silicon oxygen bond get broken and silicon fluorine bonds are produced. So this stability is the driving force for this reaction. Now, so let's come back to the fourth method for this silyl ether hydrolysis. and in this case two I am showing, one is silylenol ether and another is silyl ether. How this enol ether? In this case this methyl lithium act as nucleophile, because we know it is polar, this is minus, so attacks this silicon center and this oxygen leaves, and ultimately this enolate is generated, which is utilized later on for other chemical reaction. And in this case it produces this tetramethylsilane. Remember student, this is a volatile compound, so it comes out from the reaction medium. So this is silylenol ether. I have already discussed about this enolate chemistry. Now let's discuss another interesting example, silyl ether hydrolysis using this methyl lithium. What happens here? This is student, this is trimethyl silyl protected, and one part is alkyne, means sp hybridized. So in this case also this methyl groups attacks here, and ultimately it deprotects and produces depending on the reagent. So this is terminal alkyne is produced. So remember student, this is actually terminal alkyne protection and deprotection using this TMS chemistries or silicon chemistry. I shall come up at the end with one another example. So this thing we have learned about the basic understanding. Now let's come to examples and little interesting examples. So example number 1, deprotection in acidic medium. So this acetic anhydride medium. So in this case two property. First of all, acidic properties because of acetic acid, and acetic anhydride you may consider it's a dehydrating agent. So what happens in acidic medium? That silane will be hydrolyzed, which is associated with less bulkness. Okay, in case of silicon site, means silane protection, all are TMS. Okay, all are TMS, means silicon side is same bulky. Now we need to consider about the oxygen side. See, this is secondary, 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 but this is primary. So consequently hydrolysis where you can expect here, and actually that's happened student. So this is OAC part, and see, look at 90%, and what is the reaction condition? Room temperature 48 hours, means you can consider this is a mild reaction condition. Okay, and not only that, the second one where the assistance from oxygen is there, so that is also associated with this 7% conversion. Okay, so this is also another interesting example where you can see the alcohol's part bulkness playing the role. Now example 2 is the deprotection in basic medium. Previous one was in acidic medium. So what happens here? Here KOH is and methanol is taken, and obviously the hydroxyl ion is the nucleophile. So question, where the nucleophilic attack will happen? Obviously less bulky site. Okay, and in this case this is tertiary butyl diphenyl, this is triisopropyl, and another trimethyl. So which one is least bulky? This is. So you can see this one, and this is first, and the second phase this one. Okay, I just try to recall in case of base mediated method, this tips is less, means most difficult. So that's why you get here this hydroxyl, this, but this is the second priority, first is this one. So third example, that is deprotection by fluoride. Okay, as I told, this fluoride is, I like, it's best because it's a C, THF room temperature 20 minutes, how much efficient it is. And in this case, what type of functional groups are there? This is triethyl, this is triisopropyl, but this is primary. So that's why it get hydrolyzed easily. And interesting part of this TBAF is that, see, other functional groups are intact under this reaction condition, because tetrabutyl ammonium fluoride is actually a salt. So you can consider this is the salt, N plus F minus. Now a question may come in your mind that, sir, why TBAF is used, not sodium fluoride? Because sodium fluoride is relatively cheaper compared to this tetrabutyl ammonium fluoride. Yes, obviously that's true student, but in this case why this TBAF? Because sodium fluoride is actually a purely salt, and in the reaction medium is THF, organic solvent. So NAF will not be soluble in this THF solvent. But this TBAF is a phase transfer catalyst. Phase transfer catalyst or PTC, means it is soluble in both organic solvent as well as aqueous solvent. Not only that, it is actually a salt, but it is soluble in organic solvent because of this 4 tetrabutyl group. So that is the reason to choose this TBAF. And by the way, I have already discussed a dedicated lecture on this PTC. So if you don't have the idea, you may visit. Now let's come to example number 4. This example is little difficult. Please look at very carefully. In this case, we have used paratoluene sulfonic acid. So you can consider this is relatively strong acid. Point number 1. So in acidic medium, this you can say these both are similar. Triethyl silane, and this is tertiary butyl diphenyl. So this is bulky. So it will not undergo, that's sure that it will not react. Now these two, but if you look at in between, there is a group, this part. This is student alpha beta unsaturated carbonyl, and we know for a alpha beta unsaturated carbonyl there is a canonical form. Canonical form means it comes here and it's open. Consequently, what it produces, this is O minus, and this carbon having a plus charge, means this is the alpha carbon, this is the beta carbon. So beta carbon is student electrophilic. Okay. So after deprotection, means after this deprotection, what it will produce? This will produce OH. Fine. So this beta carbon is electron deficient. So through a intramolecular reaction will happen, and in this case this oxygen will act as a nucleophile, and through intramolecular reaction produce. Now question, how many member of ring formation? 1, 2, 3, 4, 5, 6, and we know 6 member ring are stable. So this side we have understood. Fine, it formation happens. Now what about the other hydroxyl group? See, it is actually student, this is actually a triple bond. So this is triple bond. So after this first ring formation, it is still now a double bond, means like this one, still the beta carbon is electrophilic. So consequently, similar way second reaction will happen, and ultimately this pyro compound will be produced. And in this case, what is the ring number? Just look at again. So this is 1, 2, 3, 4, 5. Again this beta carbon is number 6. So second ring is also 6 member. Now let's come to the example number 5. Reduction and deprotection simultaneously. What happens? See, here no fluoride is given, no acid base is given, lithium aluminum hydride is given. So what it does actually, if you look at this all functional groups, there is a OAC, means O this. Now in the next phase, what you can expect, that these O after reduction, this will be O minus. So this will be O minus, there will be hydride transfer. So these O minus, what it can do, it can attack this O silicon, because OES means triethyl. So these all are ethyl. Okay. So this is ethyl. So what it can do, this O minus can attack here, and ultimately it will come back. So ultimately now where the silicon gone from this oxygen, it goes to this part, this acetate. And we know lithium aluminum hydride finally converts an ester into alcohol. So this part, this organic part will be in alcohol part, so means this one. But because of this intramolecular reaction, this hydroxyl was deprotected. So that's why you can see this hydroxyl deprotection, whereas the other TES triethyl silane is intact. Here is also intact. So this is actually an intramolecular reaction, or you may say neighboring group participation type reaction. That's why although there is no deprotecting agent, but still during the reaction O minus is produced, or base is produced, or alkoxide is produced, which cleaved the silicon oxygen bond. So in this way the smart deprotection happened. Now so this is a common example. Now this is a very interesting example, student. Selective silyl ether formation of primary alcohol. Why this is unique? See, this is a very big molecule, I know, but this molecule, what we are actually focusing? Alcohol protection. As I told, silyl ether formation. Now where are the OH group? One is here. So this is one. Second is this one. And any other? Yes, obviously third. Now if you look at, this is actually an ester acid, carboxylic acid, so not that much nucleophilic, leave it. Now this is actually a primary hydroxyl and this is actually a secondary. So this primary is less bulky and what is taken? Triethyl silyl chloride and 2,6-lutetium as a base. Now student, look at the other condition, DCM minus 78 degrees centigrade. How much mild reaction condition is it? And yield is 97%. So how much selective? And actually in this case selective silylation happens on this primary alcohol, and you can see here, although under this reaction condition, I repeat, under this milder reaction condition, ethyl secondary, this group doesn't undergo silylation, and you can see this OH is free. Okay, so and in this case, interesting comparison, look at triethyl silyl chloride gives, imidazole gives monosilylation, just 97%, whereas if you use triethyl silyl triflate and 2,6-lutetium, both give bisilylate product. So that is the uniqueness or proof that how much this OTF is a good leaving group and how much this triethyl silyl triplet is a reactive reagent. So this is another proof of the statement. So now let's come to the last example. I know you are bored, but this is a big chemistry, I'm sorry. So in this case, LDA-TMSCl, what it produces? Alkyne, or more specifically if I say, this is terminal alkyne. So this is terminal alkyne protection. Okay, so how it produces? First LD abstracts this proton and ultimately converts into a carbon ion. So it produces this carbon ion. Fine. These carbon ion act as nucleophile. So similar like this previous one. So it attacks this carbon center via SN2 type reaction and it leaves, and ultimately it produces TMS protected thing. And by the way, we know these sp carbon hydrogens are significantly acidic compared to sp2 and sp3. So that's why this reaction possible. So remember student, not only for this silyl, means this alcohol, it can act as terminal alkene too. Not only that, there are some example also amine protection, nitrogen base, but I am not going to that much complication, so I shall stop here. So in conclusion, what you have learned today, that silyl ether formation is a good strategy for protection of alcohol. Oxygen silicon bond is stronger due to pp-dpi back bonding, and oxygen silicon could be deprotoned in presence of either acid, base, fluoride or methyl lithium, and my personal choice is this fluoride because of its milder reaction condition. So finally, the selectivity of silyl ether formation and deprotection could be achieved in presence of differently bulky silyl groups. So this gives the selectivity and advantage of this reaction. And finally, the terminal alkynes or amines can also be protected using the same principle. So let's come back to our example. This 4.4 equivalent of triethyl silyl chloride, and actually what is the reaction product? 3. Now you may think that, sir, 4.4, 4 equivalent is taken, but why 3? First of all, 3 hydroxyls are available, student. There is no hydroxyl left, and the reaction medium is imidazole DCM, means base is also present in the reaction medium. So whatever HCl will be produced during the reaction will be instantly quenched by this 5.2 equivalent of imidazole. So no acid is there, so no hydrolysis, and this is a ether, it can't attack. This is carbon iodine bond inert under this condition, so it will not react. And ultimately, so what is the option of today's discussion? Option is this option B. And now why not others? Just look at here, only one TMS, not possible. Excess silicon reagent was taken, not possible. In this case, this OMe got hydrolysis, not possible. And finally, in this case, this carbon iodine got silylated, not possible. Okay, so option B is the right answer. So this is the end of the discussion. I believe this video may be useful. Please write your opinion in the comment box and try to answer the question I have asked. And if possible, please visit my another channel. So thanks for watching. See you in my next video. Bye bye.